In this tutorial, we're going to learn how to apply a compensatory approach to making selection decisions using a multiple linear regression model in R. So just as we can use multiple linear regression to evaluate whether evidence of incremental validity exists for a selection tool, we can also use multiple linear regression to apply what's called a compensatory approach to making selection decisions. Now, in the context of employee selection, a compensatory approach refers to the process of considering applicant scores on a set of selection tools to predict who will have the highest scores on the criterion, and in doing so, applicants can compensate for lower scores on one selection tool with higher scores on one or more other selection tools. Now, one of the simpler ways that we could apply a compensatory approach to making selection decisions is simply to give everybody or to equally weight the different selection tools and their scores. However, in this tutorial, we're going to learn how to use the regression coefficients, or the regression weights in other words, to apply those as part of the compensatory process, and that way we can weight scores for each one of these selection tools empirically. Okay, so to get started, what you'll see here is we have a data file called concurrent validation, and this is a .csv or comma separated values file. I have already saved this file into my working directory folder, which happens to be my R workshop folder, which is within my H drive, and you can see that path displayed here. And so here's that file saved. So if you're working with this file or another file, make sure that you have already saved it to a folder that you can subsequently reference and within the R environment by setting your working directory. Okay, so we'll get into what this data file actually contains once we read it in. And so now let's move over to RStudio. And when you get into RStudio, we'll likely see that we've already got some text here in our console with the version number and so forth of R, on top of which, or below with which I should say that RStudio is running on currently. So we can see here we're using R version 4.0.3. I'm going to go ahead and clear out the console there. You could go to Edit and Clear Console to do it through the drop-down menus. I just did Control L on my Windows computer. I'm also going to zoom in here so that hopefully you can see what I'm doing a little bit better here when I start typing into the R script. Speaking of which, if I go to File, New File, and R script in my drop-down menus, again, that's File, New File, and R script, I'll open up my R script editor window. Okay, and the first thing I'm going to do is make an annotation here and just make a note of what we're doing here today, which is we're going to be applying, again, a compensatory approach to selection decisions using multiple linear regression. Now, if you need more of an intro to multiple linear regression and how to interpret it, check out my video called Evaluating Incremental Validities of Selection Tools Using Multiple Linear Regression in R. All right, so I prefaced this at the beginning, but let's go ahead and just remind ourselves what this compensatory approach means in the selection tool, and specifically the employee selection tool validation process. When I say a compensatory approach, I mean I'm referring to the process of considering applicant scores on a set of selection tools to predict who will have the highest scores on the criterion, where the criterion is another word for the outcome of interest, which in the context of employee selection, one common criterion variable is some type of job performance variable, whether that comes from performance evaluations or maybe some more objective indicator of productivity, for example. Okay, so the next thing that we're going to do is we are going to be setting our working directory. Okay, to set the working directory, I'm going to come down here and use the setwd function from lessR. That's setwd all lowercase, and within the parentheses type in quotation marks and then the path that leads to the folder where I just saved the data file I showed you, which was called concurrent validation. So the name of that folder is in this path. It's called my R workshop folder. It's my H drive. So I'm specifying my H drive there and my R workshop folder. I happen to remember that off the top of my head. So I'll just go ahead and click run on that line of code there, and you'll see everything worked out here in the console. I set that working directory. Alternatively, if you wanted to set it more manually through drop-down menus, you could go to Session, Set Working Directory, choose Directory, and then find the folder where you save that file and then click Open, and it'll do the same thing. Again, that's Session, Set Working Directory, choose Directory. Okay, now I am ready to read in the data file, which again is that concurrent validation.csv file. And so I'll make a note here, read in the data file. The next thing I'm going to do is come up with an object that I can assign the data frame that I read into the R environment to. And so I'm going to call that object just df, lowercase d, lowercase f, just to stand for data frame, fairly generic here. I'll use the left-handed arrow operator so I can assign what I read in to this object that I've called df here. And the name of the function I'll use to read in the data file today is read.csv, which specializes in reading in comma-separated values or .csv files. And within the parentheses, I'll type in quotation marks, and then the exact name of the file that's saved in my working directory, and make sure that you add on the .csv extension there. And so it's concurrent validation, which refers to the type of selection tool validation design that we are going to suppose that the data were collected using today. And I'll explain more on that in just a second. All right, so make sure you include that .csv extension. Click run. Looks like I typed and spelled everything correctly there. And so now it worked. And now we see in my global environment here in RStudio, I have a data frame called df, and there's 300 observations. And in this case, the 300 observations are current job incumbents or current employees. And there are 5 variables. Let's click on this object here so we can open up the viewer here and view a tab containing this data frame object that we just read in. Now the first variable is a unique identifier variable. I include this here when I simulate the data just simply to remind us that each row here represents a unique employee. And so here are the unique identifiers for the employees. Let's suppose that these data were collected as part of a concurrent validation design, hence the name of the data file. And what that means in this context is that in the employee selection tool context is that the selection tools, so in other words, the assessments that were given that we would like to eventually give to applicants to evaluate whether or not they're going to be a good fit for the job in terms of their job performance or some other type of criterion we're interested in, we are going to give those current employees, select a group of current employees, give them the selection tools we wish to validate, and then at about the same point in time, evaluate their performance or obtain some recent measure of their job performance or some other criterion we're interested in. So here you can see the variable all the way to the right here in the rightmost column is performance with a capital P. Let's treat this as our criterion variable. So this is our outcome variable of interest. This is our this is the indicator of job performance. Let's assume this is supervisor ratings of job performance from a performance appraisal or performance evaluation tool here. And let's say that it can range from a score of possibly the lowest score being 1, meaning low performance, and the highest being 30, meaning very high performance. Okay, so moving to the left here, now let's focus on the 3 selection tools. We have SJT, which stands for Situational Judgment Test, and then we have EI, which stands for Emotional Intelligence, and then Interview stands for, let's say, a structured interview here. And on all 3 of these variables, note that higher scores indicate higher levels on whatever these variables are measuring. Now, we're only going to focus on 2 of these selection tool variables here today, and that is the SJT, the Situational Judgment Test variable, and the Interview variable, which is our structured interview variable. Let's assume that the situational judgment test, the SJT variable, can range from 1 to 10. Again, 10 means higher levels of whatever that SJT is measuring. And the interview, it can range from 1 to 15. So these 2 selection tools have different scalings here. And let's say that 15 indicates that someone has scored higher on whatever this interview is intending to gather or measure. All right, so now we have oriented ourselves to the data that we're working with here today. The next thing that we're going to do is we need to install the lessR package if we haven't already done that before. If this is your first time working with the lessR package or you haven't worked with it recently, you'll most likely need to use the install.packages function. Again, that's install.packages and it's all lowercase. And within the function parentheses, type quotation marks, and within those quotation marks, type in the exact name of the lessR package, which was developed by Professor David Gerbing at Portland State University in the School of Business. And you'll see that it is lessR with a capital R. Now, I have very recently installed this, and so to save time, I'm not going to run this line of code. In fact, I'm going to annotate it out, so if I were to run the script from top to bottom at the end or all at once, I won't get bogged down by reinstalling this. It doesn't necessarily hurt things, it can just slow things down. Okay, but what you do definitely need to do, and what I definitely need to do, is to access that package. And to access the package, I'm going to use the library function from baseR. And as a sole parenthetical argument, I'll just type the exact name of the package which is lessR with a capital R, assuming that I've already installed it, which I have. And note that you don't need to put quotation marks around the name of the package within the library function. Next, I'm going to click Run. And you'll see you get some red text here in your console. If you're just opening up the lessR package for the first time in a session that you're working on, you'll notice that you do the first time that you access it, you'll see this feedback here, which just gives you the version of lessR and some other helpful information here, as well as the website if you want to see some new information, which is lessrstats.com/new. All right, the next thing that we're going to do is we need to start off, if we're going to apply a compensatory approach to selection decisions using multiple linear regression, let's start by estimating a multiple linear regression model. And to do so, we're going to use the regression function from the lessR package, hence why we just accessed that package so that we can use this function. So it's regression with a capital R for regression. Hopefully that's easy to remember. And then the first argument is we specify our multiple linear regression model, which, if you recall, a multiple linear regression model has 2 or more predictor variables and a single outcome variable. In this case, we will have 2 predictor variables and the single outcome variable. Our outcome variable is going to be our criterion variable, which in this case is a job performance variable, and here it's called performance with a capital P. And so here you can see the exact name of this variable is performance with a capital P. And then next, we're going to specify the predictor variables, which are capital S, capital J, capital T, and then interview with a capital I. Okay, so to the right of our outcome variable, type the tilde symbol. So that's the tilde symbol there. It's not a dash, that's a tilde. And then we will type our first predictor variable. It doesn't matter in which order. So the first one will be SJT, so that's SJT all capitalized, and then add the plus sign operator so that we can add an additional variable, which is interview with a capital I. So right here is our first argument. This is our regression model that we have specified and that we would wish to estimate here in a moment. Add a comma so we can add the second argument, which is just going to be data equals and the name of the data frame to which all 3 of these variables belong, which is df. Okay, we read that in here. This is the name of the data frame. So data equals df. Okay, the next thing that we're going to do is click Run here. And we're going to ignore all the plots and so forth that come standard with the regression output here. If you want to learn more about how to interpret what you find using a multiple linear regression model in terms of the various types of output, check out my other video called Evaluating Incremental Validities of Selection Tools Using Multiple Linear Regression in R. Okay, but the next thing that we're going to do is I'm just going to give you a little preview of the output and just kind of skim through until we get to a substantive part that's relevant for this tutorial here today. So we're starting with the beginning of the output here, skipping on through the background section, and we come down here to basic analysis, and we're just really interested for the sake of explanation here in this tutorial, the estimated model for performance. And so why have I stopped here? Well, let's first see what we're working with here. Here you see on the first line, this is the model intercept. So this is your y-intercept value for the estimated regression model. And then you see here that the intercept value is 5.527. It doesn't really matter that it's significant or not here. The p-value here is less than the conventional alpha level of 0.05 for a two-tailed test. So we would treat that as being statistically significantly different from 0. However, of more substantive interest, here we see our first predictor variable, which is our first selection tool here, is our situational judgment test, which is abbreviated using the acronym SJT. Its regression coefficient or weight is 0.567. The associated p-value here is less than 0.05. So we would conclude that the association between SJT and performance, which is our outcome variable or criterion, is positive and statistically significantly different from 0 when controlling for the effects of the other predictor variable we have in the model, which is the other selection tool, which is interview. Speaking of which, the last line here in this table, you'll see that the regression coefficient for the interview selection tool variable is, and its relationship with performance, which is our criterion variable or outcome variable, is 0.385, and the associated p-value is also less than the conventional cutoff of 0.05. So we would also conclude that the association between the interview variable and the job performance variable is positive and statistically significantly greater than 0 when controlling for the effect of SJT, the other predictor variable, on job performance here, or simply performance. Okay, so why have I pointed out this information? Well, we're going to actually remind ourselves that what we're looking at here are the building blocks of a regression model equation here. So here we have our y-intercept value, we have our regression coefficients or weights for both the predictor variables, and so what we can do is we can actually construct a regression linear equation here. And I want to just, for the sake of demonstration, show you what I mean by that. So using those building blocks from our output, we could type out the equation like this. Well, what we're trying to predict is performance, right? So performance is our outcome variable. So I could actually call this performance predicted, okay? Because here you can see we have observed performance is what we already collected. But ideally what we'd like to do with this type of equation or this type of multiple linear regression model, if we're using a compensatory approach to making selection decisions, is use the information that we've estimated empirically in our multiple linear regression model and then plug in new values potentially when we have, let's say, future applicants that we actually administer these selection tools to. And then we can weight their scores on each of the selection tools appropriately, add in the intercept value here, and then get hopefully what is an accurate prediction of their future job performance. Okay, so what you'll see here first is this is just the simple equation for a line. The first value here is the intercept value, which is 5.527 plus, and then the regression coefficient, the first one for SJT is 0.567, you see that here, times a value for SJT, so this would be someone's score on the situational judgment test, plus the product of 0.385, which is the regression coefficient or weight. That's the association between the interview variable and the performance variable, 0.385, and times a score on the interview variable, let's say in the future at some point, okay? So again, this is our intercept. This is our first regression coefficient or weight. This is our second regression coefficient or weight. So how would we use this equation in practice? Well, let's imagine this. I'm just going to copy it here. And let's imagine a situation where, okay, fast forward into the future a bit, and we've got some applicants. So we've decided that these tools, we've validated them, and we determined that this is the type of compensatory approach we want to use, where we're going to weight the scores on the interview by 0.385 and scores on the SJT by 0.567. And so what we can do is actually, let's say hypothetically, we have an applicant that comes through, and that applicant scores a 5 on that SJT, which I think was out of a possible 10. And let's say on the interview, they scored a 7, and I think that might have been out of a possible 15, if I recall. Yes, out of a possible 15. Okay, so let's see what the predicted score would be for that particular applicant who got a 5 on the SJT and a 7 on the interview. Well, all we're going to be doing is simple arithmetic here and following mathematical orders of operations. First, we multiply 0.567 times 5, and then we add that to the product of 0.385 times 7, and then add all of that to our intercept here. And so that will equal out to be, copy this. So if we do that basic math here, and we can actually do it in our console here, type that out, it's 11.057. So this would be the predicted future job performance for that applicant who scored a 5 on the SJT and a 7 on the structured interview using this compensatory approach. So you can see here, we're not applying equal weights to people's scores, but you can see how it's compensatory, meaning that you can compensate. Let's say if a person got a lower score on the structured interview, relatively speaking, but scored higher on the SJT, they could potentially compensate with this equation and actually have a fairly high future performance prediction. Of course, people who score perfectly on both of these tools, selection tools, will have the highest predicted scores. Okay, so this brings us to our next phase, which is how can we more or less automate this process or do this in bulk, okay? So instead of going through and what we did just here and just manually calculate this and include and plug in different values or scores for future applicants into our regression equation, we can actually automate this a bit. And I'll make a note here that now we are going to predict criterion scores. And what we're going to do is the first thing that we will do is let's go ahead and take the same regression model from above here. So we're just going to copy the multiple linear regression model code from above. And I'll make a note here that we're going to estimate, or rather assign the multiple linear regression model to an object. So I mean by that, just paste in that multiple linear regression code from above, the function from above that we specified our model in. And then to the left of it, type the left-handed arrow operator. And then to the left of the left-handed arrow operator, type in some type of object name that's unique. You can make it up. I'm going to call it reg for regression underscore mod for model. So reg underscore mod. You can call it whatever you'd like. Okay, and so what we've done here, or what we're about to do, is we are going to assign the output of this regression function here, using the left-handed arrow operator, to this object here. And this will allow us to more easily subsequently reference specific aspects or elements of that output, and we can build that into an equation. This will make more sense in just a second, so bear with me. So go ahead and click Run there. You can ignore this. This may or may not show up when you do this. This is just simply telling me that the margins are too small. If you do run into that issue and you want to avoid that error message, just open up your plot window so it's large enough so that a plot can form. Otherwise, you'll see a message here that says margins too small. It just means these, or rather maybe the plot margins are too large for this given space. Something to that effect. Okay, the next thing that we are going to do is, now that we've assigned this to an object, you can see here, if we just run the object by itself by selecting it and highlighting it and click Run, we just get our model output as we did before. We already saw this, okay? But now what we can do is we can reference specific elements from it. So we're going to reference the estimated model intercept and assign it to an object, okay? So just like we assigned the regression model to an object, now we can assign what different elements from our regression model output, which we've stored in this object here called reg underscore mod here, or reg mod for short, and we can do some referencing. So let's copy the exact name of that object. And the next thing that we're going to do is we are going to type in the $sign operator. And when you do that next to an object that's storing or contains output from a model, you're going to often get this default list here. And even if you don't get the default list, you can just type in coefficients. Okay, so I'm just going to type in coefficients here. Or you could have gone through and selected that, but it's coefficients. Make sure you spell that correctly. And watch what happens if I just run this by itself. Just highlight that and run it by itself. It's just going to pull the model regression coefficients from that estimated model section in the basic analysis. And so this is just our intercept with some more digits reported after the decimal place, our SJT, and our interview. You can see here's 0.385 for interview, regression coefficient 0.567 for SJT, and about 0.527 for the intercept, which we saw above here. So that's where those values are. Now, what if you'd like to reference specifically just the intercept value? So we don't want to request all the coefficients, just the intercept value. Well, what we can do here is add brackets and use this bracket notation here, and then simply type in quotation marks, and then copy this exact name of how the intercept is referenced here, noting that the intercept is surrounded by parentheses, so make sure you get those parentheses. Paste that all within the quotation marks there, and then click Run. And so you can see now we've just grabbed the intercept. So it's just selected from that vector of coefficients. We're just grabbing the intercept value. Now let's take that And to the left of all that, let's type the left-handed arrow operator. And to the left of the left-handed arrow operator, let's just type in B0, where let's assume this stands for B sub 0, which is a common way of writing out a regression equation. In fact, I'll just type that out here. Commonly, we might write a regression equation like this. If we have two predictor variables, we might say B sub 0, which is our intercept, plus B sub 1, which is our first predictor variable, times x, which is, let's say, the first predictor variable. We'll call the x1 actually, plus B sub 2 times x sub 2, which is our second predictor variable. And you could keep on going here. If you had 3 or more predictor variables in your model, you would just do plus B sub 3 times x sub 3, and so forth and so on. So that's what we're talking about here. So this is the notation I'm using, is just referencing the intercept. Okay, so we're going to just run this, highlight and run. So now we've stored this into this B sub 0 object. So if we click run on just the B sub 0 object here, you'll see it returns in our console that intercept value. Okay, so the next thing we're going to do is I'm going to just copy this for convenience, those two lines that we just created there, and along with the annotation that comes above it. And the next thing that we're going to do is grab specifically the predictor variable and its regression coefficient. So just get the exact name of the predictor variable, which is SJT, and then just replace what was in the quotation marks here with SJT. And I'm going to note here that we'll call this regression coefficient. So here we're referencing an estimated model regression coefficient and assigning it to an object. Okay, and we're going to assign it, let's call this B sub 1, just for to stand for the first regression weight or coefficient associated with the first predictor variable here, which is SJT. And click run to run that line of code there. And you'll see that now if we just highlight and run B sub 1 here, or B1, you'll see here is the regression coefficient or weight for the SJT variable. So that's the strength and direction of the association with the criterion, which is performance. Okay, so the next thing we're going to do is copy the two lines we just created, paste them below, and now we're just going to swap out, grab the exact name of the second predictor variable, or in other words, our second predictor, our selection tool, paste it in here. It's just interview with a capital I. And now we're going to change the object we're going to assign this interview regression coefficient to B2 or B sub 2. Click run. So now we've stored it there or assigned it to B2. And if we were to just run B2 by itself and highlight it, you'll see this is the regression coefficient that we were already familiar with that represents the sign and the strength of the association between the interview selection tool and the criterion of performance. All right, so we're getting closer now. The next thing that we're going to do is, let's imagine that we're we fast forwarded in time to a point where we've developed this regression model already based on our sample of validation data. And now let's say that we're now fast forwarded into the future, and we have access to applicants, and we're having the applicants go through our selection system. And as part of that selection system, they're completing the same SJT or situational judgment test, completing the same structured interview and being scored on it. And so they've received their scores on that. Now we need to figure out, okay, who should we make offers to from this group of applicants based on their selection tool scores, and by applying this compensatory approach based on multiple linear regression to make our selection decisions. And so here's where we plug in future values, or new values rather, that contain actual applicant data. Okay? And so the next thing that we're going to do is we are going to read in the data file, and I'll say data file number 2, and this is the data file containing applicant data. Okay, so applicants data on the SJT and the interview selection tool. So the name of the new data file, the second data file, in other words, that contains the applicant data, is called new applicants. And here we are. So it's a .csv file. And as you can see here, we have 3 variables in it. And one is an applicant ID, and this is just to indicate that we have applicants here. So these are unique identifiers for applicants, not employees. And here are their scores, each person's score on the SJT and the interview, the structured interview. And so here we have applicant AA1. They scored a 6 on the SJT and a 9 on the structured interview here. Now I've already gone in and I have saved this data file called new applicants, this .csv, into the same folder that I set as my working directory earlier on, which is my R workshop folder, and that's in my H drive. And so it's probably easier if you save this file in the exact same folder that you previously set as your working directory. And again, it's called new applicants with a capital N for new and a capital A for the first letter in applicants. Okay, so now that we have that and ready to go, we are ready to read it in. And let's go ahead and call this data frame object that we're about to assign the new data file contents to. Let's call it new_df just to indicate that it's the new or second data frame. We used the left-handed arrow operators before. We'll use the read.csv function. We don't need to set our working directory, assuming that we've saved that data file into the same folder or location as the first data file that we read in that was called concurrent validation. And so within the function parentheses and within quotation marks, type in new applicants.csv, assuming you're using the same name for that data file or the same data file. Okay, so new applicants.csv, all one word there. Click run. Okay, so now we have a second object here, or rather a third or fourth object here. So we've got new_df here, and so that's just the data file that we just saw here. Now we've read it in as a data frame object, and we've assigned it to the object called new_df. Okay, so now we are ready to plug in these new values for these applicants. And notice that we don't have the criterion variable here. We don't have job performance because these are applicants. They haven't yet performed the job. So what we're trying to do is predict their job performance scores. Okay, so to do that, what we are going to do is, I'll make a note here, we are going to assemble the regression equation and assign to a new variable in the second data frame. Okay? And what I mean by that is we're going to create a new column here in this new_df that's going to be our predicted performance scores. Okay? All right, so the first thing that we're going to do is come up with a name for that new object. And so we're going to assign it again to the new_df data frame object that we just read in. Use the $sign operator so we can attach this new variable name. So we just need to come up with the unique new variable name. So a variable that does not already appear in new_df. So we don't want to name it applicant ID, SJT, or interview. Probably what's most intuitive here is something like perf_predict. And I'm doing perf with a capital P to stand for performance and predict with a capital P. So this is going to be the new name of the variable that will appear in our new_df data frame object. Use a left-handed arrow operator so that we can assign a regression equation and the new values for the selection tools, the output of those, or in other words, the predicted values for performance to this new variable that will be attached to this data frame that's called new_df. So here is where these objects we created above, the B0, B1, B2 for B sub 0, B sub 1, B sub 2 respectively, this is where these come into play. So first, B sub 0, we type in our object where we've assigned our intercept value. Start building out our regression equation here, plus the first regression coefficient that corresponds to our SJT test, which is going to be B1 is our regression coefficient, and times, using the asterisk operator here, the name of the data frame. And here we're grabbing the second data frame, so we can grab the applicant scores for the SJT and interview. So new_df, $, and then SJT, all caps. So now we're saying multiply or weight, in other words, using this compensatory approach, the regression coefficient times the score of the SJT for each of the applicants who we have data. So each row of data here, or each observation. And again, this is the SJT variable from the new applicant new_df data frame object that contains the applicant data. All right, the next thing we're going to do is add the +sign operator and then add our regression coefficient for our second selection tool, which is B2, if you remember from above. So I'm just pulling these values here. If you wanted to make sure you get them exactly right, they are case sensitive, just you could copy and paste them here. So B2, that's a regression coefficient associated with the structured interview, times new underscore DF. So the name of that new data frame containing the applicant data, $, and then the name of the interview variable, which is interview with a capital I. So it's named the same thing as our original data frame. So SJT and interview are spelled and capitalized in the same way between the two data frames. And now we've built out the equation. If you had a third selection tool or a fourth, you would just do plus B3 times so forth and so on. You would have to make the additional regression coefficients above and assigning the specific coefficients. Okay, so you might be asking, why are we doing it this way and assigning using this notation? Well, part of the reason is for reproducibility and for making it easier. Let's say that we end up changing something about the data, so we read in different data or something like that. When we estimated the original regression model, if we use this approach by referencing specific components of the output, assuming we use the same regression model but different data with it, we don't need to update anything in our script. We just need to read in the different data. And so it more or less automates this process for us, which can be advantageous and make it less likely that we'll make certain errors and so forth in transcription of copying and pasting numeric values from our output into our equation. Okay, so we've specified the regression equation here. We're going to assign the results of the regression coefficient, which would be in vector form. So actually, let's just run the first part of the equation. So it's just the actual equation itself, what we'd use to predict the outcome here, which is our criterion of predicted performance. If we just run this highlighted section here, note that you'll get a vector, and this is in order by the different rows in our new data frame here. This is going to be what would be predicted for the person who scored here first, a 6 on SJT and a 9 on structured interview. The first value here indicates that you would expect them to have a future predicted performance of 12.399, and then you move on to the second person and so forth. So you'll notice there's 15 values here, and that corresponds to the 15 applicants. Now, if we run this all together here, watch what happens. Now we go back to our data frame object. Now we have a new variable that pops up here and has been assigned to this new underscore DF data frame object. And it's just the same values we saw in the vector here in our console now have been applied. So it's a little bit easier to understand. Oh, here we've got the person, applicant ID AA1, their predicted score is 12.399 and so forth. Okay, so the next thing I'm going to show you how to do is often when we're using such approach like this, a compensatory approach, and we're trying to predict future scores, we're going to take those predicted scores and we're often going to sort them or arrange them in either ascending or descending order so that we can pick those people that had the highest scores and then extend job offers or move them on to the next phase of the selection system, whatever the case might be. So how do we go about? We could, of course, sort here by just clicking these arrows, but that's not very reproducible if we do it that way, meaning we don't have any code that can reproduce that in a more automated way. And so how do we do that using an R function? Well, what we're going to do is we are going to first make a note that we're going to sort the data frame by the new variable in the default, and I'll note here, ascending, so smaller to larger values, order. And so I'll show you how you do that first, and then typically what you're going to want probably is going to be descending order, which is just will be a slight tweak to the code here in a second. But to do to use this approach and to do ascending order, you type in the name of the data frame you wish to sort, which is new underscore DF, brackets. We're going to use bracket notation here. Then we include the order function from base R. It's ORDER, all lowercase. Parentheses for the order function. And then as the sole argument within the order function, we'll just type in name of the data frame object that contains the applicant data that we wish to sort, which is new underscore DF, $, and what is the variable we wish to sort by? We wish to sort by this new perf underscore predict variable here. Okay, so just remember it's perf with a capital P, predict with a capital P. And so we type that in here. Perf, capital P, predict with a capital P, There we go. Now, outside the function parentheses, but still within the brackets, we need to type in a comma here. So why do we need to type in a comma to the right of the order function that we've specified here? Well, because we want to sort or order, in other words, or arrange the data by row, okay? So we're going to sort by row here. So you can see that we have row, 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 row. We're going to sort in that way. If we had put this to the right, that would mean we'd try to sort by column, which is not what we want to do here. Okay, so watch what happens when we click run here. You'll see down here in our console, we have sorted the data frame in ascending order. And you can see now that we have the lowest values for performance predict all the way up to the highest as you descend, this is ascending down here. But it's ascending from this. If you imagine this being a vector that's laid out horizontally, the values are ascending. Now, if we want to sort the data in descending order, I'll put this in asterisk 2, so hopefully it stands out a little bit more. All we do is in front of new here, so within the quotation marks, or rather within the parentheses of the order function, just type in the minus or the subtract operator here. And this just essentially does the opposite. So by doing that, if we click run, we've now sorted in descending order. And so what you see here is the people who scored the highest or have the highest predicted future performance, their scores come at the top here. And so what you see is that if we were to focus, let's say we wanted to extend job offers to the top 3 people based on their predicted performance, based on using this compensatory approach to making selection decisions, we'd start with these 3 people. So we'd talk applicant with ID number AA14, AA9, and AA12, these 3 applicants, because they have the 3 highest predicted performance here. Okay, and it's kind of interesting sometimes to look at their, like this person here, their SJT score is 6, but it looks like they compensated, hence the compensatory approach nomenclature, with an interview score of 15 out of 15. And you can see here, the second person in terms of the ranking, their score was an 8, and but on the SJT, which is greater than 6, but they scored slightly lower on the interview. Now, you might also use a banding approach or something like this. And what I'm using in this example is assuming that we're going to just rank order people or sort them in this way and then give the first offer to this person, second to this person, third to this. If they decline, you start moving down the list, and you might have a floor too where you won't go below a certain level of predicted performance. Now, if you want to make these changes quote unquote permanent to your data frame object, meaning if we come back here, so I'm going to delete, just close out those tabs here. And let's say we click on the new _df data frame, it hasn't actually been sorted in the actual data frame object. We just printed the sort to our console there. So to actually change in the data frame itself, we would just do the left-handed arrow operator, and we're going to choose the descending order here. And we're just going to the left of the left-handed arrow operator, we can overwrite the existing data frame object of new _df with the new sort by just typing in new _df to the left here. Put your cursor somewhere on the line, click run. Now look what happens if I go and I click on the name of that data frame object, new _df. Now you see we've actually changed it in the object itself. So we've sorted based in descending order the perf _predict criterion variable here. Okay, so that is one way in which you can apply a compensatory approach to making selection decisions using a multiple linear regression approach. This is again an empirical approach. It's based on the model estimates that we're using here, as opposed to subject matter expert judgments or something like that, or just applying equal weights. So there are other approaches in an employee selection context to doing a compensatory approach. But this is one of the approaches we can use, which again is based on the regression coefficients or weights that are derived or estimated from a multiple linear regression model.